Welcome to the 12th session of galvanic cells. In this session, we are going to see how we can derive the Nernst equation thermodynamically, because Nernst equation we have already discussed, and it is an equation in which we relate the EMF of the cell and of the activities or concentration of the electrolytes involved in the cell reaction. Okay. So, we will move on to the derivation. That is, we have seen that the free energy change accompanying a reversible reaction depends upon the activities of the reactants and products. Okay. Now, I am going to represent a general form of a reversible reaction, where A moles of A, small a represents the number of moles, small a, small b, small c, etc. It is a number of moles of reactants. In a similar way, we have small letter L, small letter m, small letter n, etc. They are the number of moles of products. Okay. So, the expression is A moles of A plus B moles of B plus C moles of C, etc., giving L moles of L and M moles of M and N moles of N, etc. So, this is a very general form of a reversible reaction. Now, the reaction quotient for this reaction means it is a ratio of their activities of the products and the reactants raised to their number of moles. See, you can see that Q is equal to this, you might have learned it in chemical equilibrium session, that is activity of the component L raised to the number of moles of L, that is small l. Okay. So, here what we are going to take, the activity of the component L, that is denoted as capital L, that is the component is L, and number of moles you have to raise it to that is small l. Similarly, activity of M raised to small m, activity of capital N raised to small n, and so on, divided by the reactants activity of capital A raised to small a, activity of capital B raised to small b, activity of capital C raised to small c, etc. So, these are the products of the products divided by product of all the reactants, okay, where A represents the activities of the reactants and products as indicated by their subscript and number of moles by their superscripts. Okay. Now, we know that delta G is equal to, that is change in free energy is equal to change in free energy in the standard state plus R T log to the base E, it is ln log to the base E Q, where Q is the reaction quotient. So, whatever reaction we are considering to be in a reversible equilibrium. So, you can take that to be not equilibrium, sorry, it may or may not be at equilibrium. You can take the product of products divided by product of reactants, you get the reaction quotient Q. When it comes to the equilibrium condition, we consider the Q to be the equilibrium constant. It can be either Kc or Kp depending on what are the activities replaced by concentrations or partial pressures in the case of gases. So, Q stands for any condition of a reversible reaction. Okay, it is known as reaction quotient. Only at equilibrium condition we call it as equilibrium constant. So, delta G is equal to delta G at standard condition plus R T ln Q, or we can convert that because we are considering electrochemical cells. So, we have to replace all the delta G values in terms of electrical energy. So, we get it as delta G as NFE, delta G is equal to NFE minus NFE, sorry, and delta G naught is equal to minus NFE naught, that is all. Okay. So, I am going to substitute that here, NFE minus NFE is equal to minus NFE naught plus RT ln Q, substituting for delta G and delta G naught. Okay. Now, what I am going to do is, I am going to divide throughout the equation by minus NF. So, first term divided by minus NF, this get cancelled. Okay. You will have only E. Here also minus NF, what happens is this gets cancelled, I will have E naught minus, here I do not have any NF. So, I will have to put it as RT by NF log to the base E Q. Okay. So, that is the equation written down, E is equal to E naught minus RT ln RT by NF ln Q, where Q is the reaction quotient. Now, if I am going to take an electrochemical cell, Q represents the reaction quotient for the cell reaction taking place within the cell. Okay. So, for a cell reaction, I can put this as E of cell is equal to E naught of cell minus RT by NF log to the base E of Q, okay, where Q represents the reaction quotient of the cell reaction. Okay. Now, converting it into the log, E of cell is equal to E naught of cell minus 2.303 RT by NF log Q. Log stands for log to the base 10, log Q. Okay. Now, if the temperature is at 298 Kelvin, see these factors 2.303 RT, temperature is 298 and Faradays, they become constant. So, together you can take that value as 0.0591. At 298 Kelvin, E of cell is equal to E naught cell minus 0.0591 by N log Q. Here N represents the number of electrons involved in the cell reaction. So, this is for the cell. So, you have two expressions, these are for the cell reactions. Okay. Now, when I am going to consider the electrode, here the case is different, you are going to consider the electrode. E of electrode is equal to E naught of electrode minus RT by NF log to the base E of Q, where here the Q will be the reaction quotient of the electrode reaction. In the other case I have taken cell reaction, and in this case it is the electrode reaction. So, the expression can be written as E of electrode is equal to E naught of electrode minus 2.303 RT by NF log Q, that is converting that to the log to the base 10. Okay. At 298 Kelvin, that is if I am taking the temperature is equal to 298 Kelvin, it can be written as E of electrode is equal to E naught of electrode minus 0.0591 by N log Q. Here N represents the number of electrons involved in the electrode reaction. Here it was N was number of electrons in the cell, in a cell reaction. Okay. But here it is again given as N, but here it represents number of electrons in an electrode reaction. So, that is the only difference. That is the only difference, okay, because the quotient is for electrode reaction. Now, I am going to take the electrode reaction in general. As you have learned regarding the reversible electrodes, we know that when we consider a single electrode, that is we are going to consider only a single electrode, not the cell, then we consider the electrode reactions to be reduction. In a cell, you will have to consider both cases, that is oxidation at the anode and reduction at the cathode, but we consider the single electrode, we always consider the electrode reaction to be a reduction, that is according to IUPAC convention. And therefore, a general form of electrode reaction can be written as, that is, an oxidized state combines with n electrons giving a reduced state. Okay. So, the Nernst equation will be E of electrode is equal to E naught of electrode minus 2.303 RT by NF log products by reactants, activity of the reduced state divided by activity of the oxidized state. Okay. So, this becomes the reaction quotient Q. Okay. Now, if we consider the cell to be operating under ideal conditions, you can replace their activities in terms of concentration, because under ideal condition we know that activity is equal to activity coefficient into concentration, that is molality, and under ideal conditions activity coefficient is equal to 1. So, you can replace them with their concentrations. In that case, you can put it as E of electrode is equal to E naught of electrode minus 2.303 RT by NF log concentration of the reduced state divided by concentration of the oxidized state. So, this is the Nernst equation for an electrode in the general condition. Okay. Now, let us consider the cell reaction. A moles of A combining with B moles of B giving C moles of C and D moles of D. So, these are the products. So, E of cell, this is a cell reaction, and therefore, E of cell is equal to E naught of cell minus 2.303 RT by NF log activity of C, capital C, raised to the power small c, that is the number of moles. Similarly, activity of D raised to D, activity of capital A raised to small a, and activity of capital B raised to B. These are the reactants and these are the products in the cell reaction. Okay. So, this is the Q which we had mentioned just before. Now, considering again the ideal conditions. So, we do not consider them as activities, you can directly consider them as the concentrations. So, E of cell is equal to E naught of cell minus 2.303 RT by NF log concentration of C raised to small c, concentration of capital D raised to small d, concentration of A raised to small a, and concentration of B raised to small b. That is, these are the products. You are taking product of concentrations raised to their molar concentrations divided by product of the concentration of the reactants. So, that is the value of Q which we have represented in terms of concentration. Now, what we are going to see is what is the relation between the EMF of the cell and equilibrium constant for the cell reaction. Now, we know that once the cell has been set up, okay, you can derive from that, it is a galvanic cell, you can derive from that a potential, or you will get an electron flow or the electricity from a galvanic cell. So, the reaction will go on for some time and finally, the potential drops to 0 and you do not have any current flowing out of the cell. And this is a condition at which the cell has attained equilibrium. Okay. Now, what is happening here? That is, we are having a cell, you have an anode and a cathode in a cell. At cathode, we know that the process taking place is oxidation. At cathode, the process taking place is reduction. Okay. Here, there will be the concentration of cations are increasing. Putting in square brackets to show that the concentration of cations are increasing, because the cations are being formed due to oxidation at the anode, while at the cathode what is happening there? There is occurring a reduction, and when reduction occurs, the cations take up electrons, they get reduced. So, in this case what is happening? The cation concentrations are decreasing, or we can say that the potential, since the concentration is increasing, means the potential of I will put it as potential itself. The potential of the anode increases while the potential of the cathode is decreasing. Okay. So, one goes on increasing, the other one is decreasing. Now, what happens is that a point is reached when these two potentials are equal, that is EMF of the anode will be equal to EMF of the cathode. So, what is happening here? That is, the potential of the anode keeps on increasing while that of the cathode is decreasing. Okay, that is what is explained here. When cell is operating, there occurs an increase in concentration of the component cations at the anode due to oxidation, and simultaneously there will be a fall in concentration of the cations around the cathode due to reduction. Okay. Now, what happens is the potential of the anode increases and potential of the cathode decreases, and finally, the cathode decreases and a point is reached where they become equal. And we know that the cell EMF potential E cell is equal to E of cathode minus E of anode. When they are equal, that means it is equal to 0. There is no EMF derived from the cell, and this is a condition when we have the equilibrium has been attained in the cell reaction. So, there is no EMF coming out. So, under this EMF condition, you can use the Q, the reaction quotient, to be substituted by the K, which is known as the equilibrium constant, because now there is no EMF coming out of the cell. It is not because it is not working, but it is at the equilibrium condition. Okay. So, Q can be replaced by K, and from thermodynamics the equilibrium condition is delta G naught is equal to minus R T log to the base E of K, where K is the equilibrium constant. Okay. That is at equilibrium condition, or you can put it as minus 2.303 R T log, this is log to the base 10 of equilibrium constant, and I am going to substitute for delta G naught as minus N F E naught is equal to minus 2.303 R T log K. Okay. Now, both sides we have the negative sign. I can put it as N F E naught is equal to 2.303 R T log K. Okay. Now, E naught of the cell is equal to 2 bringing that N F towards the denominator, 2.303 R T by N F log K. At 298 Kelvin, this is 2.303 R T by F becomes a constant, that is 0.0591 divided by N log K. And this expression can be used to calculate the equilibrium constant from EMF values, provided if you have a reversible reaction that you can make it occur in an electrochemical cell, and then from that measuring the EMF at standard conditions, you can find out the equilibrium constant for that particular reaction. Okay. Now, let us make it clear by doing a problem. The Nernst equation, we have already discussed all the problems along with the Nernst equation. Now, here we will have it the electrode potential and equilibrium constant problems solved here. the standard electrode potential for a cell in which the following reaction Fe3 plus aqueous combines with 2 iodide ions in the aqueous state, giving Fe2 plus in the aqueous state plus iodine in the solid state. Calculate standard Gibbs energy change and the equilibrium constant for the cell reaction. Now, the given values are E naught is equal to E naught of cell. No, the standard electrode potential for the cell. Okay, E naught of cell is equal to 0.23 volts at a temperature of 298 Kelvin, and you are given the cell reaction. Now, again in the last problem we have been finding out the value of N. Here the oxidation state is +3 of iron, but you have got 2 Fe3 plus, that makes a total of +6, right. Iodide ion, each one has got -1 oxidation state, so this becomes -2. In the case of here, this is +2, but 2 together, total change will be +4. Now, this is also for 2 iodide ions, and iodine it is 0. So, it makes no difference, that will be 0 itself. Now, let us see what is the change in oxidation states. Fe3 plus gets reduced to Fe2 plus, the change in oxidation number is from +6 to +4. That means, it has to add 2 electrons. Okay. From -2 in the case of iodine, it goes to 0, that means, it loses 2 electrons to get into 0 state. Okay. So, the value of N is 2. Once you find out the value of N, it is easy to calculate. Delta G naught is equal to minus NF E naught, delta N is equal to 2 into F is equal to 96,500 coulombs into potential of the cell, E of cell is equal to 0.236 volts. Again coulomb into volt gives you joules. Just calculate it and you will get the answer as -45548 joules. Okay. So, we found out Gibbs free energy. Now, we have to find out the equilibrium constant. For that, you can have two methods. One is you can apply this equation, delta G naught is equal to 2.303 RT log K, and log K, retaining that we are taking minus 2.303 to the other side, it makes minus delta G naught by 2.303 RT, and delta G 0 is equal to it is already minus with minus 45548. Do not forget the signs to be included, divided by 2.303 into R is equal to 8.314 and the temperature is 298, I believe. Yes, it is 298. 298. Okay. So, this minus and minus it becomes plus. Solve it using a calculator, you will get it as 9.61 into 10 to the power 7, and that is the value of K. It can also be calculated using another one, that is you need not go for delta G values, you know that E naught is equal to 0.0591 by N log K. Now, log K will be E naught into N, this goes to the numerator and this comes to the denominator. So, that is 0.0591. Okay. E naught value is 0.236. N is equal to 2, whole divided by 0.0591. This is a easier way. Now, K will be equal to anti-log of 0.236 into 2 divided by 0.0591. Okay. Here also this is log K and for K you have to take anti-log 9 point, no sorry, the values of 45548 divided by 2.303 into 8.314 into 298. I forgot to say about the anti-log portion. Okay. You have to take the anti-log, and to take anti-log what we have to do is press shift, then press log, then in bracket you give the terms to be solved. Okay. So, here also for finding out K you press shift, then press log, then put in bracket what is this, that is 0.236 into 2 divided by 0.0591, and this will give you the answer as the same what we got the above question, because the same values 9.61 into 10 to the power 7. So, do not forget to take the anti-log. Now, to conclude, we have been seeing the Nernst equation derivation, how it is derived thermodynamically for both electrode as well as the cell. For electrode it goes as E of electrode is equal to E naught of electrode minus 2.303 RT by NF log concentration of the reduced state divided by concentration of the oxidized state. When it comes for the cell, it is E of cell is equal to E naught of cell minus 2.303 RT by NF, and we assume the C and D to be the products and that of the reactants, that is concentration of C raised to small c, concentration of capital D raised to small d, concentration of A divided by concentration of A raised to small a, and concentration of B raised to small b in the denominators. So, these represents the products of the cell reaction and this represents the reactants. Okay. Then we have learned the expression relating EMF and equilibrium constant K, that is E naught is equal to 2.303 RT by NF log K. So, that is all for the session. Thank you.